angry, actually.
I'm sorry to hear that. All right, you guys. So, like I say, this is basically the last section we need to learn about this chapter. All right. Basically, what we're going to do is we're going to learn the rotational equivalent of Newton's second law. I know, right? Okay. So, in order to do that, we need to learn about something that's called rotational inertia, and see how it is tied to angular acceleration. All right. So, oh, I forgot to fix the spelling on that. All right. All right. So, last semester, one of the things we learned was that an object's linear acceleration, right, depends on the net force on the object and on its mass. In other words, we learned that net force was equal to mass times acceleration, or that acceleration was net force over mass, right? Cool? Right, now, over the last couple days, we've been talking about torque, right? And we said torque was the rotational counterpart for force. All of the problems we've done so far have been problems where your net torque has been zero, right? So we've had the things balance, okay? But what if your net torque isn't zero, all right? Well, it turns out, we talked about this already, that if your net torque isn't zero, then your object is going to rotate, and more importantly, it will accelerate how quickly it's rotating, okay? And so, sorry, my brain just paused there for a second. Okay, so what we want to do is we need to come up with sort of a rotational counterpart for this equation. Okay, in other words, what's the relationship between the torque on an object and the angular acceleration? Okay, well, it turns out that in order to discuss that, we need to talk about the rotational counterpart to mass. All right, and weirdly, it's not the exact same thing. Okay, so if you want to accelerate something linearly, its inertia, the thing that resists the change in motion, just depends on the mass. Okay, it turns out though that for rotation, that's not the case. It's not just the mass that determines sort of how hard it is to cause the object to accelerate. Okay, so sorry, I'm just trying to decide what thing I want to talk about next. All right, so it turns out that the rotational counterpart to mass, called rotational inertia, depends, as you would think, on the mass of the object, but it also depends on the shape of the object and how the mass is distributed. Okay, so here's what I mean by that. So we've got a meter stick here with a weight taped to the end, right? Okay, so what I'm going to do is I'm going to just change how quickly this thing's rotating. So right now it's not rotating at all, okay? And I'm changing how quickly it rotates, right? Every time I change direction at the end, I'm changing how quickly it's rotating, right? Okay, that's pretty easy to do. I can do this. Well, I can do it all day, but right, it's pretty easy, right? Okay. Now, if I flip it around, okay, it's not going anywhere. I can do it. This is way harder. Okay, I haven't changed the mass of the stick at all. All I've done is change the distribution of the mass. All right, and you guys, I mean, if you get a minute later on in the hour, grab this and do this. But can you guys see the meter stick's actually bending now, right? Okay, because this now has much more rotational inertia than it does here. Does that make some sense? Okay, so how hard it is to change an object's rotation doesn't just depend on the mass, it depends on the mass and the distribution of the mass. Okay? And so what we're going to learn is how to calculate what's called rotational inertia. All right? The symbol for rotational inertia is a capital letter I. All right? So before I do that, let me show you one other example that's maybe a little bit more concrete of how rotational inertia can affect an object's acceleration. All right? So one of the things we learned first semester was that, like, when you drop an object, how quickly it falls doesn't depend on its mass, right? Okay. Similarly, if I slide objects down a frictionless ramp, the mass doesn't matter, right? Okay, and you guys understand, this is a little dodgy. The wheels are simulating no gravity, or no friction, right? Okay. So watch what happens. So my two carts, one of the carts has more mass than the other. All right, if I release them, what should they do? they should go down at the same acceleration, right? So again, unfortunately, I think this one of the tracks has a little more friction. We did this a couple times before class. Try swapping carts. Why? Is physics not working right now? I'm going to be stubborn. I'm going to do it again. Okay, good. All right, so obviously, friction and the bearings are an issue, right? Okay, but so in this example, this one had twice as much force, twice as much mass, and as a result, we got the same acceleration. Good? All right, now, these two things, so this one is metal, this one's wood, they have the same mass. Okay, approximately. It's not exact, but they're pretty close. Okay. So, based on what we just saw, it seems like they should go at the same rate. Okay? But if I roll them down the hill at the same time, nope. This one is way faster. Right? Okay? And I can switch ramps and it'll still do the same thing. The solid one always wins. I don't know why I put that there, right? And the reason that this one wins is because it has less rotational inertia. It's easier to cause this to accelerate than it is to accelerate this. Right? The reason for it, well, there's a few ways we could explain it. One way would be to do some calculus, which we won't do. The easier way to explain it is this, that a minute ago I was waving this meter stick around, right? And we decided that if the mass was farther away from the pivot point, it's harder to change the motion, right? Okay? Well, when I roll the disc, basically the pivot point is the center. This has most of the mass concentrated at the center, right? Whereas this has the mass concentrated farther out, giving it more rotational inertia, meaning it's harder to cause it to accelerate, which makes it roll slower. Follow? Okay, so this demonstration that we just saw, when we get to work and energy, will become much more important. But for right now, what it illustrates is the difference in rotational inertias. Cool? All right, so then the question becomes, great, so if rotational inertia depends on not the mass, but also on the shape of the object, then how do we find the rotational inertia of an object? So, to do that, you need to turn the page.
Oh my god.
All right, let's see. Okay, so different objects have different rotational inertias. I'm glad you enjoyed that. So different objects have different rotational inertias, and this sheet gives you some samples of common shapes that we'll be dealing with. Okay? So, let me kind of run through what these different things are. All right, so if you want to calculate the rotational inertia of a thin rod rotated around the center, it's 1/12 the mass of the object times its length squared. Okay? Yes.
Yeah.
It's basically it's got to be much longer than it is fat or tall. Okay? In other words, this dimension needs to be significantly larger than the other two dimensions. Okay? And it needs to be uniform, like the mass needs to be uniformly distributed. Okay? Yes.
So these would be approximations.
Yeah. Well, actually, no. I mean, if this is uniform, that's exact. It does turn out to be exact.
Does that formula come from, do those formulas come from all the
Yes, it's a bunch of integration. Yeah. Yeah.
You have to learn this.
So you don't need to know where these come from. Okay? So like on a test, I'll give you this sheet.
Oh.
Okay? So you don't need to memorize these or know where they come from. You just need to know that different shapes have different inertias. Okay? The mass. M is mass. That's okay. I know. I don't know why they used capital M on this. I think usually capital M is reserved for a specific mass. So I think this is referring to specifically the mass of this thing. I don't know. All right, so anyway, so if I wanted to find the rotational inertia of this meter stick about the center, then I would take half of its mass and then multiply it by its length squared and then divide that by 12. Cool? Now, if I want to do it about the end, that's the second one. Okay? So this is the rotational inertia of a thin rod rotated around the end. Cool? All right. This would be if you took this, okay, rotated about the center. Cool. This bottom one we use all the time because it's a door. Okay? So the way it's drawn this way, like it's flipping up this way. But even if it's vertical, it's still the same. Make sense?
If you have, if you put it like each had it like face down, have you had the?
For sure, yeah. It would create a torque, yeah.
So
For the same reason that this tips.
are we going to be including that in problems?
Yes. How do I want to say this? All right. So Josh's question, Josh's question brings up a really good point, you guys. So in the same way that the mass of an object is a property of the object, rotational inertia is a property of the object. All right? This has a mass of 1 kilogram no matter what. Okay? Similarly, that notebook that I was just flipping around has a rotational inertia of some number, no matter what forces are acting on it. The forces are going to affect the torque, which will affect the acceleration. Does that make sense? Does that clarify? All right. So this one we'll use a lot. Anytime there's a door or a gate or something, this is the equation you use. Now notice, you guys, to calculate the rotational inertia of they call it a plane or a slab, it's 1/3 mass times a squared. And notice the drawing. The a is the width of the door. Okay? It's not the acceleration. All right? So this thing is a box, or sorry, a rectangle that is a units, whatever, wide by b units long. And notice, this dimension doesn't matter at all. Okay?
Wait, so what's the A?
Is that because A
Acceleration.
is different distance from the
Exactly. Sorry?
So what is it?
This dimension.
Okay. The short side.
No, it's not necessarily the short side. It's the side that's perpendicular to the axis.
Okay, got it.
Does that make sense, you guys? So if I was to find the rotational inertia of this door over here, once it opens in, but whatever, then A there would be the width of the door this way. Make sense? It's basically the radius of the curvature of the outside. Good? All right. All right, so those are all kind of squarish, rectangle-y shapes, and then over here we've got roundy shapes, right? So, solid disk, 1/2 mr squared. Hoop, mr squared. They have the same mass, same radius. Which one did we say had more inertia?
The solid.
twice the hoop.
The hoop had more inertia, right? Because it doesn't have the 1/2, right? Hello? Liam? You sure? Christine?
What is this opposite of linear?
How do you mean?
It's like, well, more fast,
More mass means more inertia, means that it would move slower with the same force, right? So if I've got 2 shopping carts, an empty shopping cart and a full shopping cart, and I push them with the same force, the full shopping cart is going to move slower, right? Same thing. This is my full shopping cart. It has more inertia, and so it goes slower. Does that make sense?
Would it have a smaller mass than a solid?
These two things?
Yeah.
No, this is metal, this is wood, so they have the same mass.
Oh, okay.
Yeah, exactly. So this has the mass concentrated on the outside.
What if they were both made out of wood?
It turns out that it doesn't matter. The hoop will always lose. Yes, that is true. I stand by that answer. I'll be able to prove that to you better once we do conservation of energy. Okay. But for now, any disk and any hoop in a race, the disk will always win because of well, a few things. But yeah, leave.
Why is the full shopping cart?
Say that again.
Why is the full shopping cart?
Because the hoop, so look at these two things. Both of our objects have the same mass and the same radius, right? So in this example, my hoop is going to have more rotational inertia. Just like the full shopping cart has more regular inertia. Make sense? Good or no? Was that a genuine O, Abby, or was that a... Okay, everybody good? All right. So, so then there's these two spheres. This is a solid sphere, like a bowling ball, minus the holes. And this is a spherical shell, like a basketball. Okay, hollow, in other words. Cool? So, and again, notice the one that has the mass concentrated on the outside has the bigger inertia, right? Because 2/3 is a bigger fraction than 2/5. Okay? So the farther your mass is from your pivot point, your axis of rotation, I guess I should say, the more inertia it's going to have, the more rotational inertia it'll have. Good? Questions about this?
No.
This is all really intimidating right now. I think once we start doing some problems, you'll be like, oh, that's not too bad. All right, now, one other quick thing. Just occasionally you'll hear, so I'm going to call it rotational inertia. High rotational inertia. You will occasionally hear people call it moment of inertia. And in calculus, you may have calculated moments of inertia. It's the exact same thing, just a different term for it. So and even up here it says moment of inertia. It seems like moment of inertia is sort of the old term for it. People are starting to more and more call it rotational inertia, just because it is more of an intuitive meaning, you know? So, all right. Everybody good with this? All right. So, what this gives us then is the rotational counterpart for Newton's second law. So, Newton's second law tells us net force is mass times acceleration. In other words, inertia times acceleration. So now our new equation is net torque is rotational inertia times rotational acceleration, or angular acceleration, right? Okay, and to clarify what you were asking about, Christine, this, remember, is acceleration equals net force over mass. Bigger mass, smaller acceleration. Here, if you rearrange this guy, you get alpha equals net torque over rotational inertia. More inertia gives less acceleration. Okay, so it's the same exact concept, just rotational instead of. Does that help?
Yeah.
Bigger mass. Bigger thing always go.
All right, are we good, you guys? All right, so I think the best thing for us to do then is to just dive in. We're going to do two examples, all right? I don't remember which one's which, but in one of them we're going to calculate the net torque, and in one of them we're going to calculate the angular acceleration. Okay? So one of the problems we're going to use this equation, one of them we're going to use this equation. All right? So here we go. Example number 1. It says if a car's tires have a radius of 33 centimeters, so I'm going to write down what I know, R equals 0.33 meters. Notice I converted my units. And an inflated mass of 10 kilograms. Then find the net torque needed to accelerate the car. So we're looking for our net torque needed to accelerate the car from 0 miles an hour. What is that a measure of, you guys? Initial linear velocity, right? And we're trying to get up to 60 miles per hour. So that's my final in a time of 6 seconds. And it says, you may treat the tire as a solid cylinder. Why did I give you that piece of information? So you know which one of the formulas to use. So let's see, solid cylinder. That's this guy, 1/2 mr squared. Now, is that going to be truly accurate? It's not perfect because the distribution of the mass isn't uniform, but it's our best approximation, okay? All right, so I'm going to write that down. I is 1/2 mr squared. Cool? All right, so to find my net torque, we've learned two equations now for net torque, right? Force times distance. Is that going to help me at all here? No, because it doesn't give me any information about how much force is being applied to the tires to make them spin. So that's not going to help me. The other one is I alpha. Well, I can find my I, so if I also find my alpha, then I'm done, right? Make sense?
Yeah.
All right, so thoughts about our path to solve this thing?
Use a jumper equation to find.
Yeah, look, we've got all these linear values. We can use these to find linear acceleration, and then use a jumper to find your angular acceleration. Follow? All right, so let's see. Somewhere we got to convert miles per hour to meters per second. We might as well do that now. So 60 miles an hour is the same as 26.8, I think. Come on, you guys, you know. Why don't you know that? All right, yep. 26.8 meters a second. Is everybody okay with the fact that I didn't write down the conversion for that? Is everybody good? Okay. All right. So here we go. So we can find our acceleration. So acceleration is VF minus VI all over T. So let's see, my VF is 26.8 meters a second. My VI was 0. My time is 6 seconds. So I divide by 6. And you get a linear acceleration of 4.47 meters per second squared. No, I did that using this calculator that I'm holding. No, that's okay. Is everybody good? All right. So jumper. Now we got to use a jumper equation, right? So let's see. So A equals alpha R means that alpha is A over R, right? So my A is 4.47 meters per second squared. And my radius, oh, I already know that, it's 0.33 meters. Divide that. So divided by 0.33 gives you 13.5 radians per second squared. That's my angular acceleration. A quick comment, you guys, this is just like a bookkeeping problem-solving strategy thing. As you find stuff, label it, because later on we're going to need this value, right? So don't just write down 13.5 radians a second squared, write down alpha equals, so that later on when you need that alpha, you've got it written down. All right, everybody good so far? All right, we are 2 steps away from being done. I think we've done the hard part, right? So are there questions on what I've done so far?
No.
Okay, so now what do we need to do? Yeah, we gotta find I, don't we? So let's see, where can we do that? So I is 1/2 mr squared. So that's 1/2. The mass of the tires is 10 kilograms. The radius is 0.33 meters. Don't forget to square it. All right, and so the units you get are weird. You're going to get 0.5. I'm going to just keep all my digits here. 0.5445. And what are the units going to be, guys, using dimensional analysis? What do we get? Kilogram meters squared. No, it's not. It's, yeah. All right. It's a 10 kilogram, sorry. It's a kg. Sorry. Everybody good or no? What's wrong?
So angry today. Angry.
Yeah, come on. Oh, totally. Yeah, absolutely. Yeah, I mean, ultimately, where we're headed is we got to use this equation. Net torque equals I alpha. So we had to find I, we had to find alpha. Yeah. I probably should have, since I went through all that problem. That probably would have made more sense. All right, everybody good? All right, so now we just multiply, right? So that's going to, let's see, our I is 0.5445 kilogram meters squared, times our alpha is 13.5 radians per second squared. So times 13.5, and it gives you 7.3, I got 7.35, but whatever, 7.35, and the units do work out to Newton meters. Because you've got kilograms, meters squared per second squared. Okay, and remember your radians kind of cancel out because they're sort of built into this I here.
Kilogram.
That's not what I wanted to do. Where's mine? I'm trying to. Oh, here it is. Ah, it's so big!
7.35
And you get Newton meters.
Newton meters.
All right, are we good? Any problems? All right. So that was one more way to find the net torque. Everybody's happy, yes? Okay. Last example.
Here we go.
Okay, so in this one we're going to go the other way, and we're going to deal with Josh's question from before about do we need to worry about gravity. All right. So what we're going to have here is Roy's attempting to lift a large piece of plywood that's sitting on the floor. So here's a less dramatic demonstration of it. Big chunk of plywood. All right. He's going to, let's see. It's got dimensions of 1.5 meters by 3 meters and a mass of 60 kilograms. He's going to grab the short side of the board and lift it like that, okay? So imagine doing that with a piece of plywood, right? So first of all, in this problem, it's rotating. So my pivot point is determined, isn't it?
Yep.
Like up until now, I've been able to pick my pivot point wherever I want. Now I have to pick my pivot point right here, right? Does that make sense? Okay? So, what we're going to do is we're going to figure out the angular acceleration when he uses this force of 300 newtons. We're going to figure out what the acceleration is when he lifts it this way versus him lifting it this way. Which one do you think is going to give the bigger acceleration?
Don't we not know?
You can make a guess. Which way is there more rotational inertia? When the mass is farther away from the pivot point or closer to the pivot point? Farther away would be more rotational inertia, right? So my guess is that this way will give us less acceleration, and this way will give us more acceleration. Okay? But let's try it and see if I'm right. Okay, so Roy's attempting to lift a large piece of plywood that's sitting on the floor. So here we go. The uniform board is 1.5 meters wide, 3 meters long, and it's got a mass of 60 kilograms. He grabs the short side of the board. So let's see if we can draw this thing. We're doing on time. We're okay? All right, so here we go. Oh, stupid green. So at the beginning, he's grabbing the short side of the board. So this is going to be my force from Roy. There's my axis of rotation, right? This is 1.5 meters. This is 3 meters. Does that drawing make sense?
Oh, we've got ourselves a parallelogram.
You guys understand that's supposed to be a three-dimensional drawing?
Yes.
It's like sticking out of the board. So here's your vertical axis, and then there's a... All right, are we good or no?
Wait, I don't.
I'm kind of wishing I rotated the drawing.
Okay, let's do it now.
It's masterful. I see no flaws.
Everybody good? All right, so the only reason I drew it this way is because we're going to need to use this to calculate our I, right? So here's what we know. the mass of the board is 60 kilograms. It's a slab, right? So our I is it 1/3 MA squared? Is that right from the sheet?
Yeah.
So which dimension is A?
Uh,
Be careful too.
3.
3, right?
How now?
Because it's the side that is perpendicular to your axis. So I drew my axis back here. So this side has to be A.
Yes.
Does everybody see that? Okay. So it's going to be 1/3 of 60 kilograms times A, which is 3 meters. Don't forget to square it. So you get 20 times 9 gives you 180 kilogram meters squared. So that's my I. Cool? All right, now what are we trying to find here, you guys? The angular acceleration, right? The fish thing, the angular acceleration, alpha, if you care what it calls. So, what other thing do I need to know to find alpha? The net torque, right? So, I'm going to make a new drawing. So here's the board laying on the ground. Here's the pivot point that he's going to pick it up at, right? So it's going to go this way, right? There are 2 forces on the board. There's the force of Roy, which is 300 newtons.
Is this like
Yeah, so this is a side view. So you're looking at it now. So the original, I should have done this before. So the original drawing was this, right? And now we're looking at it this way.
So wait, what was the original? Sorry.
The original one was this.
Right. Okay. Yeah.
Everybody good? All right. So what other force is acting on this thing apart from Roy? Gravity. Where should I put my force of gravity? Right at the center of mass, right? So here's my force of gravity. So that's going to be 60 times 9.8, right? So negative 588 newtons. Good or no? I have the multiple of 9.8 memorized up to... No, just up to 12. All right, so let's see, my 2 distances. So this distance here is going to be 3 meters, and this one's going to be 1.5 meters, right? Follow? Is everybody okay, or no?
Yep.
This? It's because... Where's my thing go? So the board is like this, right? This side is 3 meters, this side is 1.5, right? So it's pivoted here, and he's lifting up at this end. So his force is being exerted at one end of the board. It's pivoting around the other end 3 meters away.
Oh, and you put 1.5 out.
That's where, yeah, the 1.5 is where the force of gravity is. Gotcha. That, okay. Yeah, shoot. I see why you're confused.
I get it.
Okay. Yeah, does everybody see that? This 1.5 is half of 3. It's not the other dimension of the board. Cool? That is how you will rewrite this problem, or this example for next time. All right, so I think we can do this then, right? We're almost done here. Let's see. So let's find our net torque. So our net torque is the torque from gravity plus the torque from Roy. So let's see, the torque from gravity is going to be negative 588 newtons times 1.5 meters. Positive or negative 1.5 for my drawing? Positive. Plus the torque from Roy is 300 newtons times 3 meters. Good. So this is going to give us negative 882 Newton meters plus 900 Newton meters gives us a net torque of what, 18 Newton meters? Are there questions about how I got that net torque?
Now we can go to find.
So now we've got our I and our torque, so we can find our L. So let me pause for a minute. Is everybody okay with what I've done so far?
Yeah.
Okay, so then we're just one step away from being done. So alpha, oh, why is it green? All right, so alpha is net torque over I, right? So our net torque was 18 Newton meters. The rotational inertia was 180 kilogram meters squared. So divide it and you get 0.1, and the units work, you end up getting radians per second squared. Cool? Correct. Yep. Yes. Yeah, that's a good point, you guys. To use this, the Newton's second law, the torque equals pi alpha, your alpha has to be in radians. Why that hadn't occurred to me. Let's say that.
Oh.
Yeah.
So for the next part, we're gonna.
Yeah, we don't have time to do the next part.
Is it always gonna be proportional like that though?
No, not necessarily. That the numbers here worked out nicely because
So you
I.
could say that since the side is twice as long, the
A little.
acceleration is twice as long. Or let's say the short side.
Well, you gotta be careful though because your torques are changing, but so is your rotational inertia. You know what I mean?
Yeah.
Because your A has changed now, and your lever arm has changed. You know what I mean?
Well, yeah, I was just thinking it's like it's like this for half.
Right.
That's why.
Right.
Or the acceleration is so.
Right. I don't know. I have to write it down. All right. So you guys, my suggestion is we didn't do the last example. It's the exact same thing tonight. All right.
Just for you.
Oh, I'm done recording. Thank you for reminding me. Yes.